now be talking about a stochastic timeline game. I will be talking about groups, about walls, about timelines, and it is going to be a semi-dynamic model in the sense. It is semi-dynamic in the following sense, as we had before. There is a stochastic process, which is of course dynamic, the state is dynamics, but the control is not dynamic, it is just taken once for all in the beginning and it remains constant. We now describe the problem. A content creator J has a set Mj of friends or followers. Now each member of the social network, say member I, has a set Ni of sources that it follows. Content from source J is created according to some Poisson process with rate or intensity parameter lambda J and sent to the timelines of all the members in Mj, that is all his followers. We define the total rate of content creation in the social network, which will appear on the timeline of node I as capital lambda I. And we further define capital lambda I with index minus j, the sum of rates from all players other than j who follow node I. Now we are interested in the stationary probability, πij, of finding a content of source j on the timeline of user I. Assume that at time 0 there is an arrival of some content C from J to I, and therefore to the set of friends Ni of users I. All these can see it. Each future arrival to I of content will push the content C further down in the timeline. After k such shifts, the content will not be any more on the timeline of user I. To analyze the presence of content on timelines, we define an ij busy period. It is the time period that starts when a content from J first arrives to the timeline of a user I, till the instant when there is no more content from J on the timeline of user I. We denote this by capital Tij bar. Let the timeline of user I have a constant size of Ki. When content C arrives, it is said to be on the top of the timeline, that is at position Ki, and at each new arrival its position gets decremented or shifted by 1. Let Tijk be the time from the moment that C, the content from J on the timeline of I, is in position K on the timeline till the timeline of user I has no more content from J. Then the busy period, the Ij busy period, is simply this Tij evaluated at point Ki. The reason we introduce these Tijk is to compute the expected Ij busy period using the following recursive procedure. Here is the recursion in terms of Tijk. The expected busy period Tijk plus 1 can be written as the sum of 3 terms. The first term is the expected time till the next content arrives at station I. The second term concerns the event that the next event is an arrival from J. In that case, a content from J appears now on the top of the timeline at position Ki, and therefore the remaining busy period is expectation of this Tijk. This occurs with probability lambda j divided by capital lambda I. The third term concerns the case in which the next event to occur is an arrival to the timeline from a source other than j. The probability of this event is the ratio between lambda I minus j, capital lambda of course, divided by capital lambda I. If this is the event that occurred, then the remaining expected time till there is no content from j on the timeline is simply Tij of k. So here is how one solves this equation. First note that there are three different arguments of Tij here. Capital Ki, small k, and small k plus 1. So we want to get rid of this. So there are two ways to get rid of it. One is at the boundary. At the boundary we simply get rid of it by taking small k plus 1 equals ki, and then we have an equation with only two different times ki and ki minus 1. And the second thing to observe is that for other points than the boundary, if we take the difference of this equation, so this is the k plus first equations, if we take the difference between this and the kth equation, then we get, in terms of the differences between Tijk plus 1 and Tijk, we get only two different times. The term with capital K disappears when we take this difference. So here are more details. We first substitute small k equals capital Ki minus 1. And then we obtain the following simpler equation with only the two different arguments of Tij. So the expected value of Tij Ki minus the expected value at Ki minus 1 equals 1 over lambda I minus j, capital. So already in this equation 1 we get a difference between Tij evaluated Ki and Tij evaluated Ki minus 1. So we'll define this difference as Sijk and we'll rewrite a simpler recursion for this Sijk. So now we shall take the difference between the two equations that we had there, and we simply get that Sijk plus 1 is alpha times Sijk, where alpha is the ratio between capital lambda I minus j and capital lambda I. So this allows us to write an explicit equation, solution to the recursive equation, which is Sijk plus 1 equals alpha k times Sij1. And the boundary solution of this equation, the boundary condition for this equation is obtained from equation 1 that we saw before. It was simply that the Sij Ki is 1 over capital lambda I minus j. So combining the two last equations allow us also to find Sij at the other extreme boundary, Sij of 1, which is written in the first equation here. We now can combine this with the relation from the previous slide that related Tijk plus 1 and Sij1. So combining these two equations now allow us to write Tijk in an explicit way. So combining these two equations allow us to obtain the following expression in equation 2 for the expected busy period. Recall that the expected busy period is just the time it takes from the arrival of a type J content till there is no more content in the timeline from source J. After a busy period, there is an empty period, which is simply exponentially distributed with parameter lambda j. It is the time till the next arrival occurs from source j. Its expectation is given by 1 over lambda j. The fraction of time during which there is content from j on timeline is therefore the busy period divided by the busy period plus the empty period, in expectations, of course. The probability to find content from j at node I, at the timeline of node I, is therefore this ratio, which gives us an explicit expression in terms of small lambda j divided by capital lambda. In the special case that the timeline is just of size 1, then Pij equals simply lambda j over capital lambda, which is the dissemination utility of the Kelly mechanism type game. We now introduce other criteria for dissemination utility. The one we used so far was this time stationary probability to find at least one content from j at the timeline of I. Now, since arrivals occur according to a Poisson process, this probability turns out also to be the one seen by the arrivals. This property is called pasta, pasta is the acronyms of Poisson, arrivals, C, time, average. We shall next consider as dissemination utility of source j. Instead of Pij, we shall consider the expected number of contents from that source on the timeline in stationary regime. We next compute the dissemination utility for this model. The probability that an arrival to I is from source j is given by lambda j divided by the sum of all lambda k's. And now this is true for any arrival of content from j to I. Therefore, the expected number of individuals from source j on the ith timeline is the size of this timeline, ki, times this qij, this probability. So now we can formulate the game. We allow for acceleration factor as before, and effort that one does in order to be more visible on the timelines. And the cost for acceleration is also, as before, some constant time, aj minus 1. Then the utility for player j is given by ki times lambda jaj divided by the summation of lambda k ak over all players k, minus the acceleration cost, which is g of aj minus 1. This is again the Kelly mechanism. It is the same as we saw already in previous talks. Here too we can use the pasta theorem in order to conclude that the expected utility at stationary regime is the same as the one we computed at arrival instance. If the arrival process were not Poisson distributed, then we would have a different utility at stationary time than at arrival times of contents. Now, why is it important and how do we use it? Which should we use? Which type of criteria? The time stationary or the one that we compute here on arrivals? An individual I observes his timeline or his wall at an arbitrary time. There is no particular time instance in which it watches the wall. Therefore, the criterion that corresponds to being visible by an individual is that which corresponds to the utility at stationary time. In addition to walls and to timelines of individuals, we have groups to which members of the group can send content. A member of the group in Facebook receives a notification when a new content is posted in the group. If it is interested, it would then watch the content at that time. Hence, in a group, one typically watches content shortly after an arrival of a content occurs. So what we argue is that these two situations can be quite different unless the arrivals occur according to a Poisson process. Now, a Poisson process is a very smooth process, a very regular process. There are sources of content which are more bursty. So what should we do then? The expression for the dissemination utility at arrival instant does not require Poisson arrival, in fact. So the situation that we have for groups holds also for Bursty or any other type of arrivals. It holds whenever the arrival times from different sources forms a stationary ergodic process in which the probability that an arrival is from source J is given, if we take into account acceleration, is given by lambda j aj divided by the sum of lambda k ak over all players k. Here lambda j is 1 over the expected time between arrivals from source j before the acceleration. Thus we can use Kelly's mechanism game and apply it here to competition in the case of groups, even if the arrival is not Poisson. But in general it will not correspond to the utility of a player to publish on the wall of an individual, since the individual watched the wall not according to the arrival of content, not at these times, but at any arbitrary time. Poisson processes are considered to be quite regular. There are other processes that can be much more bursty in practice. When we describe, for example, creation of videos on breaking news, when there is an event, from time to time there will be bursts of videos from different news sources. So what we want to analyze next is how does burstiness influence dissemination utility of users. Before computing performance measure related to bursty creation of content, we shall introduce some properties of exponential random variables. This will help us understand the intuition of the results that we shall get. So assume that we have two random variables, x and y, which are exponentially distributed with parameters r and s respectively. We first note that the probability that x is greater than a plus b, condition that we know that it's greater than a, is simply equal to the probability that x is greater than b. A very simple calculation shows this, in fact. I will not go into the calculation themselves here. So let x denote the time at which some event occurred. So if this event occurred after time a, then the remaining time till that event will occur, till time x, is still exponentially distributed with the same parameter. This is what is known as the memoryless property of exponential random variables. Here x is said to be memoryless. So this is the first important property that we shall need later. Then we have some properties that we already saw. Probability that x is greater than y, when they are both exponentially distributed with parameters r and s respectively, is equal to r divided by r plus s. Another interesting property here is that the probability distribution of z is independent of whether this minimum z is attained by x or by y. So the probability that the minimum is greater than q and that it is achieved by y equals to the product of the two events. I'll now briefly discuss the bus station paradox, and the reason is that on one hand I want to introduce some new concepts, the forward and backward residual times. And on the other hand, I would like to give you some intuition to the difference between publishing on the timeline of a group or of an individual. Assume that the times between arrivals of a bus to a station are exponentially distributed with parameter s. Hence, the expected time between arrivals of buses at the station is simply 1 over s. This is directly obtained by computing the expectation with respect to the probability density function of exponentially distributed random variable. Now, assume that we arrive at the bus station at some arbitrary time. Due to the memoryless property of the exponential distribution, the time that remains to wait till the next bus is also exponentially distributed with parameter s. This remaining time is called the forward residual time. One similarly defines the past residual time as the time that elapsed since the last bus arrived at the station. This variable is also exponentially distributed with parameter 1 over s. So here is the paradox. The time between the arrival of the last bus and the next bus is 2 over s, because there is 1 over s till the next one comes, and 1 s over s since the last one arrived. But this is just twice the value, 1 over s, which we computed, of the expected time between arrival of buses. One defines similarly the past residual time as the time that has elapsed since the last bus arrived at the station. It is also exponentially distributed with parameter s. But then the time between the arrival of the last bus and the next bus has as expectation 2 over s, which is twice the value of 1 over s which we computed in the previous slide. So this is the paradox. We shall now explain the paradox, where this difference comes from. There are two types of inter-arrival times between buses. The inter-arrival times that we see when we arrive at the station is called the time-stationary inter-arrival time. The inter-arrival times seen when the bus arrives are called the palm-stationary inter-arrival times. The time-stationary inter-arrival times are always larger than the palm-stationary one, since the longer the time period between arrival is, the more it is likely that we arrive during that time. Thus, there is a bias to longer periods between buses. So the conclusions from the paradox is that there are two different types of distributions always associated with inter-arrival times. One is the stationary one, which is the inter-arrival time as seen by someone that arrived between these two arrivals. And another one is the inter-arrival seen at the moment of the arrival. So at the moment that the bus arrives to the station. And these two gives quite different quantities. And therefore, in modeling a problem, we should always be aware that there are two different distributions, and we should know to which one the problem at hand corresponds to. So the next thing I would like to do is to give you an example which illustrates the difference in the context of social networks. So we shall now consider a competition between two independent sources. One will correspond to a smooth arrivals of content, the other to bursty arrivals of contents. So let U and V be two independent Poisson processes with parameter R and S respectively. UM and VM are the time of the mth point of U and of V respectively. Recall that U is Poisson with parameter R if and only if the time between successive points are IID exponentially distributed with parameter R. So we now describe the Bursty model. Let n be some integer greater than 1 and assume that S equals nr. So the parameters of the S and R of the Poisson variable are such that S is larger than R by an integer factor of n. Source 1 is assumed to be smooth in the sense that at each point UM, one new content is created and arrives to I. Source 2, which is more sparse, is assumed to be bursty. So at each time Vm, there is a creation of simultaneous burst of n successive contents. Now note that both processes have the same average time between the creation of two successive contents. And this is given by 1 over S. We are interested to see how burstiness impacts the dissemination. Our performance measure for source J is the stationary probability Pj of finding no content from J on the timeline of I. So the dissemination utility is just 1 minus this probability. Now the probability that last arrival of content was from the smooth source is given by Q equals S over the sum of S plus R. And since S is just n times R, remember that, then this gives Q equals n over n plus 1. Now if the last k posts to I were from the source which is smooth, this means that the timeline of I is full with these content. So there is no one from the bursty source. So the probability that there is no content from the bursty source equals the probability of the event that the last k consecutive content were from the smooth source. And this is simply q to the power of k. So p bursty is q to the power of k. The probability that the last arrival of content was from the bursty content is 1 minus q. So it is 1 over n plus 1. The stationary probability for finding no content from the smooth source in the timeline of I is then given by 1 minus q to the power of k over n, which equals to n plus 1 to the power of minus k over n. So to see the advantage of being smooth, consider, for example, k as some constant a time n, and we shall take n tending to infinity, getting large. In that case, P smooth goes rapidly to 0 as n increases, whereas P bursty converges rapidly to a positive constant, exponent of minus the constant a. In other words, for large n and large k, larger n means large burstiness, large k means large timeline. So when they are both large, then the probability to find in the timeline content that originates from the smooth source tends to 1. But this is not the case with the bursty content. It can be as small as we wish if we take the constant a to be small. The conclusions of this part of the tutorial are that there are differences in the way an individual wall is sampled by its owner and the way a group's timeline is sampled by the group's members. If we compare two sources of content with the same average rate of creation of content, we see that content of the more bursty source are less seen on individuals' timelines. However, if we consider timelines of groups, there is no difference between the two.